Okay, so right now, kind of the schedule is, we're going to have a assessment over this whole periodic tape thing, either Wednesday or Thursday, depending on kind of how today goes. So, you just might want to keep that in mind. You're also going to, I've got this to give you, which will make sense later on. So here is, and we'll talk more about this later, but this is also kind of a summary. So this periodic table does nothing but show you what happens to the atomic radius, and it's like a visual thing. So obviously, as you go down a group, groups go up and down, periods go across. So as you go down a group, what's going to happen is that those are going to get bigger and bigger and bigger. So you're adding like layers to an onion, because you're adding, you know, hydrogen only has the first energy level. You get to period 2, now you're into the second energy level, third, the fourth. So remember, these numbers out here tell you the highest occupied energy level. So anything in group 4, the highest occupied energy level is going to be the 4th. If you're in the 5th, that's going to be 5s, 5p, whatever, okay? So that's a shortcut way of doing this. Now, down here, and we'll talk more about this later in the week, the difference between cations and anions. So remember, the cations are formed by losing electrons. And that's typically what happens with metals, because they only have 1, 2, or 3 outside electrons. Like having 3 goats, it's like, they'll just give up the goats as opposed to trying to take in any more. So cations are formed by losing electrons. Anions are formed by gaining electrons. And those tend to be your non-metals, like oxygen, fluorine, chlorine, bromine. Okay, so those in the top right-hand corner of the periodic table gain a stable configuration by taking in goats. The metals, which is the vast majority of the periodic table, form stable ions by losing electrons. So what you'll see here is that it compares the size of the anion of the atom itself to the ion. You'll just see the cations become smaller, anions become larger. We'll talk more about this later. So I'm just going to give this out so you have this as a reference. This is also, because it really didn't make a whole lot of sense, but here's this big, I've sent this to you in Google Classroom, but this is this big packet, and basically what we're going to do, and we've done a lot of this, but like for example, we're going to talk about atomic radius, and we'll go through what I want done out of this. I don't want this whole thing done. I'll tell you specifically what I want done out of this. So stop that while I hand this stuff out. So yeah, go ahead. So eventually, we're going to do a lot of this. If you want a head start, so like for example, we haven't talked about on page 3, we haven't talked about Lewis structures yet. We will. So a lot of this, it's kind of a hodgepodge the way this thing was put together, and I didn't get a vote. But a lot of this will kind of make sense, like we're doing the lab. So a lot of this is kind of review, because it talks about writing electron configurations. We haven't talked about Lewis structures yet, and I wouldn't get too wrapped up in kind of doing this, mainly because I'm going to show you like the shortcut way to do these electron configurations, because it's all about the outer valence electrons anyway. So if you look like on where was it? On page, even on this first page too. So let me kind of show you the shortcut way of writing electron configurations, because it's going to save you a lot of pain and hassle. So if you look at, and this is kind of the central idea of what happens on the periodic table, and what scientists figure out was that over here you have the noble gases of helium, neon, argon, krypton, okay? And these elements were actually one of the last ones to ever be found. And the reason that they were the last ones to be found is because they're inert, which means they don't react. So imagine that you're at a party and you have the very dynamic people, you know, they're out running around dancing, you know, putting lampshades on their heads, you know, taking selfies, all this good stuff, making TikTok videos, okay? And, you know, like let's say, for example, not that she would do this, but let's just pick Emma as an example, okay? So Emma's at the party, she was wearing lampshades, she's doing this stuff. And it's like, hey, was Emma at the party? Oh yeah, she was there, man, she was reactive. You know, she was interacting with everybody. People were going to know that Emma was there, okay? Now, on the other side of the coin, let's say that Grace is at the party. Grace is just sitting back, just kind of watching people, okay? She's not interacting. She doesn't need anything from anybody. She's just chilled out. And then it's like, a week later, it's like, hey, was Grace at the party?
It was.
Maybe, I don't know, okay? So Grace is going to be hard to detect because she doesn't react with anything. So even if you look at the element helium, okay, the element helium got its name from the Greek word helios, which means sun. So actually it's a weird story. The way we figured out that the element helium existed was that we looked at the spectrum of light that was emitted from the sun. And, you know, we talked about spectrums, and each one has like its own individual, like, you know, fingerprint, like lines of color. And when they separated the light from the sun, they found a series of bands and a spectrum that didn't match with anything that we knew about on Earth. Okay, and this was like in the late 1800s. And I was like, well, this is just kind of weird. Like, here's a spectrum of something that we didn't know about. And so it was later on that they actually found the element helium. And so that's why they call it helium, because it comes from the Greek word helios, which means sun. Now, helium is obviously very important. And actually, in World War I, they used helium because it's very, very light, lighter than air. They used that to fill up these large airships. And so there was actually a huge stash of helium in southwest Kansas. And they actually kept that as a national secret because they didn't want people to know that we had that stash of helium because of the fact that they were using that to fill up the airships for World War I. So it was actually, they kept it secret. Now, this is going to be my small tirade, okay? The problem is the Earth only has a limited amount of helium, okay? And once we run out of helium, we can't make any more, okay? You wouldn't think it would be difficult to make. It's like helium, come on, seriously. It's 2 protons and 2 neutrons. How difficult can that be to make, okay? Unfortunately, it's very, very difficult to make. Because of the natural repulsive forces, like you have to have temperatures and pressures basically mimicking the sun to take hydrogen and smash it together and make it into helium. Now, the cool thing about it is if we ever can pull that off, we have unlimited supplies of renewable energy. Because number one, hydrogen is the most abundant universe, or element in the universe. And without going through a whole lecture on nuclear fusion processes, basically what happens is you take 4 hydrogen atoms and you combine that into a helium atom, okay? Hydrogen is 4 protons. So basically when you do this, there's a little tiny loss of mass that gets plugged into Einstein's equation, E equals mc squared. So if you were to put a helium atom on one side and the 4 hydrogen atoms on the other side, the helium atom would have a tiny bit of less mass. But this is the speed of light, which is 3.0 times 10 to the 8th meters per second, and that's going to get squared. So that gets you to the 16th right there. So it doesn't take very much mass at all to produce a tremendous amount of helium. So this is one of the things that you all might see in your lifetime, is a fusion reaction process that takes hydrogen, smash them together under extremely high pressure and extremely high temperatures, and you get helium out of it. You also get thermal energy in the form, because E equals mc squared. You can use then to heat up water and spin a turbine, and then you can make electricity, and then you can make toast, okay? So, but right now it's theoretical, they're working on it, haven't quite been able to pull it off right now, because right now it takes more energy we have to put in more energy into the process than we get out. So it's like an energy negative situation right now, but they're working on it. So when you all get ready for graduation and birthdays and things like that, I beg of you, don't tell people don't use helium-filled balloons, because here's the reason why. We only have a certain amount of helium in the Earth, and we have to have helium to run MRI machines, which are magnetic resonating images, because they have to have really, really cold. Helium is the coldest liquid on Earth. So we have to have liquid helium for that. So that's why don't use helium-filled balloons. Number one, because it's a train wreck, they have to be in Mylar. Mylar doesn't decompose, so what's really irritating is that people go, oh, we'll do a balloon release and we'll have helium-filled balloons, okay? Number one, that goes up in the atmosphere. The helium comes down, it lands eventually. So you've wasted the helium. Then you have the Mylar balloons, which land on the Earth, and they never decompose. Like, it takes like 10,000 years for a Mylar balloon to decompose. It just pollutes the atmosphere, pollutes the world. So don't use helium-filled balloons. It's just train wreck. Keep the helium. Let's use it for MRI machines to help people as opposed to your helium-filled balloons. There's my soapbox. I'll get off of that right now. But here's the whole point of this story, is that elements want to be like the noble gases. So let's say, for example, I asked you to write the chemical symbol for sodium, okay? The electron configuration. So here's the old way of doing this, okay? 1s2, 2s2, 2p6, 3s1. Okay, that's the old school way of doing this, and it's a long, arduous process. Here's the shortcut. If you look at the electron configuration of neon, which is 1s2, 2s2, 2p6, okay, that's the electron configuration of neon. So basically what happens is that sodium wants to look like neon by losing an electron. So the shortcut way of writing an electron configuration, if you want to do sodium, what you do is you put a neon core, which takes the place of the 1s2, 2s2, 2p6. So you put a neon core, and then you write 3s1, okay? So that just saves you that whole process of writing those out. So this is the beauty of why you have these numbers out to the side. So let's say, for example, you want to do, calcium, okay? So what you do is you go to the period up above, you find the noble, and you can only put noble gases as the core. That's the only thing you're allowed to put. You're only allowed to put noble gases as the core. So if you want to do calcium, you come up here, you go, oh, I'm going to put an argon core 4s2. If you want to do iron, okay, so iron is 26. So you go an argon core, and then you're going to come over here and you're going to go 4s2, and then count across 1, 2, 3, 4, 5, 6, 3d6. Okay, so that just saves you a lot of pain and suffering, and it's a much faster way to write those electron configurations. So you just put but again, listen to me. You can only put noble gases as the core, okay? And everything still has to add up. So argon has 18 electrons. So if I take 18 plus 2, that gets me 20, plus another 6, that gets me 26. So your total number of electrons still have to add up to the atomic number of the element, okay? So that's another way that you can check that you got it right. Does everything still add up to 26 or whatever that atomic number is? And then if you go across, and let's say you've got gallium. Oh, okay, you got 3d10, 4p1. So then you can come over here and go, oh, 4p1, 2, 3, 4, 5, 6. So it's all about the noble gases. So that's just a shortcut way of doing that. Anyway, all right, so let's talk about the lab that you're going to do today. So it's kind of it's a guided but yet not guided lab. How about it, if that makes sense? So one thing, first off, on this background information, which I strongly suggest that you read, So there's a typo, and it says, you're talking about the group 4 elements, okay? So your group 4 elements are carbon, silicon, germanium, tin, and lead. So there's a typo down here where it says among the group 4 elements. That should say both tin and lead, not time, okay? That's why I hate using other people's stuff. Anyway, so that should say tin and lead, not time. Time doesn't make any sense. Time has nothing to do with this. That should say tin, okay? So I'm just telling you. So this goes back to the whole idea that Mendeleev knew certain chemical properties. He knew about relative atomic mass. He knew their phases, were they solids, liquid, gases, and he knew how they reacted. So what the beauty of what Mendeleev did, again, is that he left spaces. So let me kind of explain what's going to happen on here. So there's some pre-lab questions, even though you think they put the pre-lab questions at the beginning, but they don't. So one of the things that Mendeleev did is he predicted this missing element he called Eka aluminum. So they knew about aluminum, okay? So if you look on your periodic table, and I want to clarify this because this is a little bit confusing because they talk about like 3 different groups in this particular lab. And I want to make sure everybody's cool with what we're talking about here. Because remember, you got to pay attention to the terminology. Groups are going up and down, okay? When I talk about a group, I'm talking about a vertical column on this periodic table, not a horizontal, vertical. Periods go across, groups go up and down. So on this pre-lab question, so this is one of the things that you got to do. There's graph paper back there. So what they did is they looked at the trend in density, okay? So you've got the density of aluminum, okay? Period 3, okay? It's 2.70 grams per cubic centimeter. And then you've got indium, which is down here. So you've got aluminum here. And then you've got indium. So there's actually a gap between aluminum and they left a gap, and there's indium down there. So that has a density of 7.31. And then down here on thallium, down below there, okay? So you got thallium down here. And that has a density of 11.85. So what you want to do is you're going to make a graph, and you can just take like a half piece of paper and do this. It's not a big deal. So pretty much you're going to make a graph, and you're going to put the period number here, okay? Okay. And this is not group number because it doesn't make any sense to put group number because they're all in the same group. So you're going to put period number here, which is basically going to be 3, 4, 5, and 6. Okay, so it's pretty, and you want to spread this out as far as you can. So you can go 0, 1, 2, 3, 4, 5, 6. Okay, right, like this. And then over here you're going to have density. Okay, and you're going to plot these points, and it should be, you should see this is, look, y'all studied math. Did they talk about linear regressions? Y'all ever heard? So I talk about linear regressions. Do you know what I'm talking about?
Slightly.
Okay, linear regression basically just means that this line has a specific slope. Okay, so linear regression just means that you could, if you know 2 points and a third point, you could figure this out to guess what the missing point is. So that's all that means is linear regression. Okay. So what you're going to do eventually is you're going to draw that graph. Okay. And then when you get down here to number 2, it says use your graph to predict the density of what's the predicted value. So you're going to come over here and you're going to find this missing value, which is going to be for gallium. So you're going to go here for period number 4, come up here, see where that line crosses the graph, come over here and find the corresponding value of that density. Okay? If you're really a math nerd, okay? If you're really a math nerd, you could write this as a linear function y equals mx plus b. If you're really hardcore, quick refresher of y equals mx plus b. What does the b represent? Y-intercept, right? So you could extend this line out here and you could find that y-intercept. M is going to represent what? Slope. How are you going to find the slope of the line? Pick 2 points. Change in y over change in x. X is going to be your period number. Y is going to be your corresponding density. Okay? If you've ever seen the movie Back to the Future, one of the lines is like, he screws it up, he's talking to the girl, and he goes, "You are my density." And it was like, it's supposed to be destiny. So, whatever that was a old joke about if you ever want to impress a girl, and she happens to be a science nerd, you say, "Oh, you are my density." She'll find that cute, or she might not. I'll leave that up to you. So, anyway, so if you're hardcore, write this as a slope-intercept form. Plug in the corresponding value of x, come up here. If you're not a hardcore math nerd, just come up here, find out where it crosses the line, come over here, and do it that way, okay? I don't care, it's gonna be a number. So here's the heart and soul of this. So, what known element in the periodic table corresponds to eco-aluminum? It's pretty simple, not a big deal, you can look up that. So then you're going to look up the density of the modern element in a reference source and record its actual density value. So all you have to do is go out on the internet, hey, what's the density of indium? It's all going to be pretty much the same. And then here's the heart and soul of this. You're going to calculate percent error. Sometimes I always call it experimental error. So and we're going to use this a lot, okay? So this is an absolute value, and it's your actual minus your predicted, and this is on your sheet, divided by actual times 100. We put it in absolute values because that way we don't have to worry about negative values. So basically, it's going to be the difference between what you got versus what you should get divided by the actual value. So your actual value is this, what you're going to get from the internet, okay? Or this is the actual value itself. So here's the reason why we do this. Mathematically, we do this because of one main reason. And let me give you a simple example. So let's say that I asked Luke to measure the length of this table, okay? And let's say the accepted value of this is 1.3 meters, okay? So Luke measures it, he gives me the paper, he writes it down, and it's 2.3 meters, okay? So Luke is off by 1 meter measuring the length of this table, okay? Meter is about like, yeah, he's off by 1 meter. I was like, man, that's horrible, okay? Man, you're supposed to get 1.3 meters and you got 2.3? That's horrible. So like, I got faith in Luke, okay? All right? Taught his mom. I know his genetic code. It's like, Luke, you can do better than this. So I'm going to give you a chance to redeem yourself. So Luke, I want you to measure the distance from Mays High School to the surface of the moon. I want that number tomorrow morning. Luke goes, I'm on it, Mr. Burkamp. I will accept your challenge. So Luke is up all night. He's got Oreos and, you know, Mountain Dew, and he's high on caffeine, and he's struggling, and he's got meter sticks and transits and yo-yos and all this stuff, okay? He walks in tomorrow morning. He has a bags underneath his eyes. And it's horrible. He slaps down a piece of paper, and he goes, Mr. Burkamp, this is what I got. So I look at it. He's off by 1 meter. It's like, whoa, that's cool, right? So in both situations, he's off by a meter. Situation number one, it's like, you suck. You're off by a meter. You're measuring the length of this table, okay? Situation number two, you're off by a meter and you're measuring the distance to the moon. Man, you are a measuring savant, okay? So in both situations, you're off by a meter. But in one situation, that's pretty good. Another situation, that's a train wreck, okay? So this is what this formula actually makes you do. is that it says, okay, how are we going to take this into account, okay? How do we do this as a percentage? And that's how we multiply it by 100. Okay, now, what we're actually gonna do in the lab, okay? So, over here on this, what you are going to do, and now, we're gonna shift. So now we're going to go to, over here, now we're going to shift to group 4. So the first set of questions, we were dealing with group 3. The second set of questions, we're going to deal with group 4, silicon, tin, and lead. So here's what we're going to do. It's the same process, but you're going to have to get a little bit creative. So what you're going to do is that you're going to have available to you lead shot, lumps of silicon, and tin shot. Shot just means that they're round pebbles, okay? So here's what I'm going to kind of guide you, but yet you're going to be on your own if this makes sense. So what you're going to try and do is that you're going to try and find the density of these materials. The problem is that we can't accurately measure the volumes of these materials, okay? So what we're going to do is we're going to take advantage of the idea that these materials will displace a known volume of water. So for example, you're going to take and you're going to measure out a mass of lead, okay? Obviously do this before you put it in the water, okay, because you want it to be dry. So you're going to come in here and you're going to measure a certain mass of lead. You're going to get that number by itself. Then you're going to have a graduated cylinder filled with a known volume of water. Okay, this is what you have to figure out. Okay, how full are we going to fill the graduated cylinder? I don't know. That's what you have to figure out. Then, so you're going to record that volume on that graduated cylinder. Use the precision that you can of that graduated cylinder. So let's say that let's just make sure everybody's cool with this. Let's say this is 30, and let's say this is 40. And each mark, and there are 9 marks in between. Okay, so I want to make sure everybody's cool with what we can do with this. If that's 30, I'm just giving this as an example. Let's say this is 30 and that's 40. How much does each mark represent? Ella. There's 30, there's 40, there's 9 marks in between. How much does each mark represent?
1.
1. So in this situation, you're going to know for certain the whole number of milliliters. 30, 40. Okay? Then you're going to, let's say that mark, and remember, when you measure the level of the liquid, always measure from what's known as the bottom of the meniscus. The meniscus is the bottom of the curve, okay? And sometimes that's more pronounced depending upon the size of the graduated cylinder. But you're always going to measure to the bottom. So let's say that this is right here, and that's halfway between 36 and 37. So if that's halfway between 36 and 37, how are you going to record that? 36.5. Yeah, 36.5. So when you're recording measurements, you want to make sure that you are consistent on the decimal place values. So if your device, and that might be something that you decide right from the beginning, depending on which measuring device that you use, and it pretty much says, hey, use a 25 milliliter graduated cylinder. Oh, okay, right, we've got that 25 milliliter graduated cylinder. First thing that you want to decide is that how precise are you going to record those measurements? So if you know you can go to the 10th, every measurement that you have has to be to the 10th place. So if it's, let's say that you want to fill this thing, again, I'm just using it as an example. Let's say that you want to set the initial volume to be exactly 30. Well, if you do that, then you've got to record that as 30.0. Okay, you have to be, it's one of the most important things when you're doing labs. you have to be consistent. Because here's the problem. If you record that as 30, and the next measurement you record is 36.5, it looks like you're using two different measuring devices. Because this one, it looks like you only know to the nearest whole number, and this one, it looks like you know to the tenths place. So you can't express different precision in your measuring device because it looks like you're using two different devices when in all actuality, you're just using the same one. So what I would recommend, as soon as you get in there, figure out one of the things that you have to decide is, hey, what are we going to do for the precision of our measuring device? So you're going to fill this up to a certain mark. I don't care where you fill it, that's up to you. You're going to add the lead shot, see how much it goes up, so you can know the mass of the lead shot. You're going to know how much it displaces. Boom, you're going to have that data. So you're going to do that with lead, silicon, and tin. Okay? So, got that idea. So here's what you're actually going to hand in. And this is kind of be a guided kind of thing. So, you've got your Chromebooks, okay? So what you want to do as a lab group, okay, you're only going to hand in one per group. And I don't want, by the way, I don't want like a group of 4. At most, well, there's 14 of you. I want 7 groups of 2, all right? I don't want a big group of 4. I want 7 groups of 2. You all figure it out, okay? Big group of 4, not happening, okay? There's 14 of you. 7 groups of 2, do the math. So what you're going to hand in, and I've kind of given you this as a guided thing. You're going to have a title. You know my titles. I get fairly creative with this. You're going to say, hey, here's going to be your title. So, beginning question. So basically what you're going to try and do is a similar type thing to what we just talked about. You're going to go to group 4, and you're going to know the densities of silicon, tin, and lead. So these are going to be the 3 elements that you're going to deal with. What you're going to do is that you're going to find the densities through experimental procedures of silicon, tin, and lead. Knowing that, then you're going to draw a graph, just like you did on the pre-lab questions. Oh, we're going to draw this graph. It's going to be a linear function. Then you're going to predict the density of germanium. Based upon your graph, you're going to have a predicted value of germanium. You're going to say, this is what it should be based upon our data. Then you're going to compare your predicted value to the accepted value of germanium. Okay, so that's the big heart and soul of this thing. So you could say something clever like, you know, our journey to germanium. Okay, density is our destiny. Okay, I don't care. Come up with a clever thing. I don't want to be bored when I grade these. Make me laugh, make me smile, make me think, wow, you all are kind of creative. Okay? Don't just come up with density lab. Boring. Okay? Bad. Okay. So then, you're going to have a procedure. Okay? This procedure, now let me explain how I want this procedure done. Listen to me, listen to me, listen to me, listen to me, listen to me. When you write this procedure, so help me God, do not write this as a paragraph. Okay? You're going to go step 1. You're going to do this. Step 2. You're going to do this. Here's your guiding light. Ella should be able to take her lab, give that to Carter. Carter should be able to walk into this lab, not know anything that's going on, and replicate her results. That's the mark of any good procedure. So when you're writing this, you're not writing it for you. You're writing it for someone else, okay? So do not, I repeat again, do not write this as a paragraph. You're going to go step 1. For example, your first step might be measure out 25 grams of lead. Step 2, fill a graduated cylinder to a certain mark. Step 3, add the lead shot. Step 4, record the value of the water after it's displaced. Step 5, things like this. Do not, so help me, if you write this as a paragraph, I'm just going to throw your lab away. No, horrible, stop, okay? Write this in a step-by-step procedure. And that's why what it says right here, okay? Then, you're going to have a data table, okay? Guess what? You're going to have silicon, tin, lead. You might have the mass. You might have the initial volume of the graduated cylinder. You might have the final volume of the graduated cylinder. You might have the volume of liquid that is displaced. Okay? That's what's going to have here. Now, you need to set up a graph. If you want to draw this out, if you want to let the computer do it, if you're keen with how you set up a data table and make it graph it, that's cool. If you just want to go old school and draw it out, that's cool. So, notice along the bottom, you're going to have periods. Periods, remember, go across. And then you're going to have density. Make sure your graph has, like for density, are you working in grams per cubic centimeter or are you working in grams per milliliter? It's the same thing. But tell me what that is. Okay, so the whole idea of this is kind of like this formal write-up. And this first one is pretty simple. It goes through this claims, evidence, reasoning. Did you all do that like as in biology or freshman? Mm-hmm. You all familiar with that process? Okay, claim, evidence, reasoning. Basically, this is pretty simple. The claim is, hey, gallium should have this specific density. And then the heart and soul of this tends to be the evidence, okay? And it pretty much takes you, here's some things that you want to address. This is why I gave you this sheet. It's kind of a guided thing. Here are some things that you want to accept. And then the reasoning, okay? And it says, hey, restate the claim. Explain the relationships between variables and why behind the science. And all you have to say is that, hey, density is a common thing that we can measure, and knowing the densities and where it is on the periodic table, and it's a linear, I would at some point in here I would use the word linear function. That density is a linear function of period. Okay, say something like that. Again, you're going to calculate the percent error. What would have caused the percent error compared to experimental values to accepted value? Now, when you're trying to explain what could have gone wrong, here's the one thing you are not allowed to ever use as a reason why it went wrong. Human error, train wreck. Okay, it is way too nebulous. Okay, you just cannot say, "Oh, it was human error." That's the lamest excuse ever for why something went wrong. Human error is not acceptable. Okay, you could say, "Hey, maybe we assumed that the density of water was 1, maybe that was off. Maybe we misread our graduated cylinder. Maybe it was actually bigger, maybe we misread it." Okay? Things like that. What you cannot say is human error. That is, you explain what that human error looked like, but you just can't say that it's human error. Okay, I'm done. So we're going to go down there. Here's what you want to focus on right now, because we can work on this other stuff back in here. What you want to do first is get your data. What I would suggest is that you divide and conquer, okay? On here, you've got, okay, and it tells you 35, 8, and 25. So that's about, okay? You're going to have scales. You actually want to write down those actual values. Don't sit there and spend 10 minutes trying to get exactly 25 grams, okay? 24.87. Get something close to that because you're going to have that shot. So what I would suggest, you have a partner. I would send someone to start getting these measured values, okay? It's like, hey, you go get those and you write down what those masses are. Have somebody else get out the graduated cylinder, decide how full you're going to put that graduated cylinder, figure out the reading on that graduated cylinder. Then I'd actually get your data. So collecting the data itself is going to take you like 10 minutes, okay? So Make that happen, all right? So here's what I want. Listen to me very carefully. The pre-lab questions, those you answer on your own. Listen to me. The pre-lab questions, everybody is going to do those on your own, on another sheet of paper. This is not typed. These you do, I repeat, on your own. Grab a sheet of graph paper. I'll give you the graph paper. This is a pretty simple graph. I'm going to just cut this graph paper in half. I will give you the graph paper for this. These you do on your own, okay? The procedure itself is going to be typed, and we'll see how we get today as far as when that's going to be due. But you're only going to hand in one per group on that. Got it? Good? Let's go.